Now, if you compare a tandem cell that has maybe 50% efficiency, you compare that to a silicon cell that has maybe 20% efficiency. So these cells are much more efficient, which means they convert much more of the light into electricity. So that's one of the advantages of these devices. The project that we work on actually tries to leverage some of the low-cost, high-efficiency solar cell with thermal storage. One of the problems with solar is always when the sun is gone, the light goes off essentially, right? So you have no power anymore. So you want to store it somewhere. So people are starting now to look at using solar cells with solar thermal receivers. So you take part of the spectrum, you use that to heat up like a molten salt or something to very high temperatures. You put that in storage tanks at high temperature. So when the sun is down, then you can recover the energy that you have stored in terms of temperature and run, for instance, a turbine or something like that. So you can extend the power generation in such a system. I mentioned the optical interconnects. If you go further there and you extend into the mid-infrared range, you're actually looking at sensing applications. And the reason is that you have molecular vibration bands in that longer wavelength region, so you can identify those, and you could identify, for instance, eventually pollutants in the air, toxins. You could, in liquids, you could detect components. But for that, again, you have to build devices. And so we're looking into making new light sources that reach into the mid-infrared. So we're working on what is called frequency combs. So these are light sources that have emitters, or that emit at multiple wavelengths in a large range of the spectrum. And so you can then use that to probe and essentially have a new spectroscopy that is on a very small chip that you can detect any kind of toxins, pollutants, whatever you're looking for. It's more sensitive, it's disposable, it's extremely light, uses very little energy. So you can run it, for instance, with a regular cell battery, or you can, in remote areas, you can move it around very easily. Right now, that's not possible. These systems are very large. You have to put them on cars or trucks to get the kind of detection that you want. So you want to have actually a reliable light source that reaches into the mid-infrared region, and that's one of the biggest challenges. You have some light source, and when we talk about light source, we talk about lasers. So you have some lasers, but the tuning range is very small. So you have, for instance, quantum cascade lasers. They go up to 6, maybe 10 micron, but you can't tune them in a very large range. So you would need a lot of those lasers, and they're today fairly large. Some have to be cooled. So that, of course, is not so good for your power requirements. So we're working on something that's much lower cost and reaches across the whole spectrum.